Hello and welcome back to the course on artificial intelligence. Today we're going to talk about the Bellman equation. It's quite a complex topic, and we're going to introduce it in a step-by-step manner throughout this whole section of the course. So we're not going to just jump straight into the most complex version of the Bellman equation right away, but instead we're going to introduce it slowly in order to gradually understand how it works. And I hope you're cool with that approach. If you are, let's get straight into it. So we're going to have a couple of key concepts that we're going to be operating with. And these concepts are S stands for state. So the state in which our agent is, or any other possible state in which it can be. A represents an action that an agent can take. So an agent can have access to a certain list of actions, and actions are very important when they're looked at in a state combination. So when you're in a certain state and then you look at actions, then it starts to make sense what's going to be the result of those actions. Because if you look at an action by itself without a state, it doesn't really make sense because you don't know where you are and where you can possibly end up in. Then we'll have R, which stands for reward, and that's the reward the agent gets for entering into a certain state. And gamma is the discount factor. And we'll talk about the discount factor in a second. It'll all make sense just now. But let's just take a note, make a mental note that we are going to have this letter gamma that we'll be operating with later on. So the person behind the Bellman equation is Richard Ernest Bellman. He was a applied mathematician and came up with the concept of dynamic programming, which we now call reinforcement learning, or which we call the Bellman equation now that's what we call now. And in 1953, he came up with that concept. And that's when the Bellman equation came to be. So let's have a look at how this all works. There's our lovely agent in the bottom left corner, and he is in a maze. And this is quite a classical maze where you've got some blocks. The white blocks are blocks in which the agent can step into. The gray block is the one that is just not accessible. So that's like a wall in this maze. The green is where the agent should be aiming to end up in. That's where we want the agent to go. That's the finish. And the red is a fire pit. So if the agent falls into the fire pit, he will lose the game. So in the fire pit, the reward, which is R, is -1. So that's our way of telling the agent that's not something we want you to do. Like, remember an example of when we're training dogs, we want to tell them like bad dog if it's not doing the right thing that we want it to do. Same thing here. We want to tell the agent that this is not something that you should be doing. It shouldn't be ending up in the square. So every time it does end up in the square, it'll get a -1 reward. So it will be punished with a -1 reward. On the other hand, if it ends up in the green square, it'll get a +1 reward, meaning that that is what we want it to do. So those are the two rewards that the agent can possibly get. And how does it learn how to operate in this maze? Just like in that example of the robot dogs that learn to walk, we're just going to let it know. We'll just tell it that here are the actions you can do. You can go up, right, left, or down. Those are the 4 possible actions that you can take. And that's it. Have a play around with that. See what you can come up with. So the agent might go to the right. Then they might go more to the right. They might go back to the left. They're just randomly pressing these buttons and they're trying to see what happens. Then they go back here, they go up, go down, go up, go right. So for now, they haven't learned anything. So far, nothing's happened. They go right, and then bam, they end up in the green square. So they realize, wow, I just got a +1 reward. So as soon as they stepped into the green square, they got a +1 reward. And that triggers the algorithm to say, okay, that's really cool. I am rewarded for ending up in this square. So I want to end up in this square. So what does that mean for the agent? That means it starts to ask the question, how did I get to this square? What was the preceding state I was in, and what action did I take to get into the square? And then it looks back and it says, okay, so the preceding state was this one. It turns out to be valuable in that state, the one that's marked with the red arrow, because from that state, I'm just one step away from getting the maximum reward I can possibly dream of +1, like a biscuit for a dog. From as soon as I know if I ever am in that state, that square marked with the red arrow, all I'll have to do is press right. So how do I tell myself, how do I remember that that state is valuable? Well, to me, there's no difference actually. As the agent, there's no difference in whether I am in the green square or in the white square, right? In the green square, I get the reward of 1. So I'm going to mark for myself that the white square for me, it has the value of 1 because it leads exactly to reward 1. So as soon as I'm in the white square, I know I'll just take one more action, I'll be in the green square, and I'll get a reward of 1. So that's why I'm going to say that the value of this square is equal to 1, because it leads directly without any sort of subtractions. As soon as I'm in here, I know my reward will be 1. So I'm going to mark this square as v equal to 1. That's the value. That's the perceived value of being in this state. Next, the agent's going to be like, okay, so how did I get into this square? And, he might walk around again and so on, end up in this square again and be like, okay, how did I get into this square before that? And the way I got into this square was from this square. Interesting. Okay, so as soon as I get into this square, I know that all I have to do is go right, and then from here I already know that I'm going to win. I know exactly how everything's going to unravel from here, and I know the value of being in this state is equal to 1, and since there's nothing is stopping me from going from here to here, the value in this is going to, the perceived value, I'm going to value being in here as v equal to 1 as well, because as soon as I'm in here, I know I'll be here, and I'll be here pretty quickly, so I'm going to win. And then how did I get into this square before that? Well, I got into this square from this square. So the value, a similar approach, the value of being here is also equal to 1. And so on. So the value of being here is equal to 1, and the value of being here is equal to 1, because each one of them leads to the next one and leads to the finish line. So that's all pretty logical at this stage. This is us pretty much designing the Bellman equation right now. So we could possibly think about designing an equation that helps an agent go through the maze. So look at the reward, then the preceding state, give it a value of equal to reward, the preceding state, and so on. So it kind of creates this pathway. It's all great and well, but the problem here is, okay, what happens if our agent, for some reason, starts in this state? Instead of starting here and taking these actions, but it actually starts in this state. How does it know? How does it remember which action to take? Should it go right or should it go down? Or should it maybe go left or should it go up? How does it remember which is the next continuation from here? If the only values it has is these values of equal to 1. So it cannot see what's further away. It can only see, all right, what I have here and what I have here. How does it know which way to go? Well, at this stage, it doesn't. It's pretty identical for the agent which way to go. And so that's why this approach doesn't really work. It's a very simplistic explanation. Of course, there's much more to it, but in an intuitive way, that's why we kind of just carry on this value backwards like that, because one of the reasons is once the agent is in between these two values, where is it going to go? It can get confused like that. And so how do we solve this problem? What are we going to do here? And this is where we're going to start introducing the Bellman equation in its actual form, slowly, step by step. So the Bellman equation looks something like this. So we've already talked about V, the value of being in a certain state. S is your current state or any given state. And there is S as well. And S prime is the state, the following state, the state that you will end up in after this state, and by taking a certain action. But we know that there's many actions that an agent can take, and that's why we've got this max over here. So by taking an action, what will happen to an agent? So let's say we're in state S. By taking an action in state S, and we take action A, what will happen is we'll instantly get a reward by getting into a new state. And remember that reward can be 1 or +1 or -1 if it's at the end of the game, or it can be a 0 if it's throughout the game. In this case, our reward throughout the game is 0. So that's the reward. Plus, we will get into a new state, which has value of S prime. So that's the value of the new state. And gamma. We'll talk about gamma in a second. But the point I'm trying to raise here, or the point I'm raising here, is that we've got many different actions that we can take. And that's why we've got the maximum. So by taking action, we get a reward, plus we end up in a new state. And so for in our case, we have 4 possible actions. For every one of the possible 4 actions, we're going to have a equation like this. So this is going to have a value they will have a different value for every one of the 4 actions. And we're going to look at only the maximum because, of course, the agent wants to take the optimal state. So if he's in state S, he's going to look at these values. He's going to find the maximum based on the action and going to take that action that leads to the maximum of these values. So hopefully that makes sense why we're taking the maximum here. Then once we've got the reward and the value of the state, why do we have this gamma parameter here? Well, it's there exactly to solve that problem of where the agent doesn't know which way to go because it cannot, it's comparing the values of two states on both sides and they're the same. That's why the gamma is called the discounting factor. So we're going to have a look at that in practice now to better understand it. So let's take our formula. We'll put it here on the top right. And now we will analyze what the values of the different states are. And every state here is a square now made. So any one of these white squares is a state, and we were going to calculate the value of being in that state. So let's start with this square. What is the value of being in this state? Well, we need to take the maximum of this value across all actions. And we know that this value is maximized as we get closer to the finish line. That's how it's constructed. And just by looking at it, you can see, because here it's got the reward and here it's got a discounting factor multiplied by the value of the next state. And it just makes sense that that's how we would construct that equation. So it makes sense that from here, the maximum of this value will be if we move to the right. So that's how we calculate the value of the state. This value of this state is equals the maximum, or equals to this value if we move to the right, if we take an action of moving to the right. So what will this value be? Well, the reward of moving to the right is equal to 1. And regardless of what gamma is, we don't have a value in the state because we are already in the best state possible. So this is the final state. It won't have a value. We just get a reward here, and that's the end of the game. So the value will be of this maximum will be equal to 1. And that's why value of state S here is equal to 1. Now, things get interesting when we move to the left, when we move backwards a bit. So now let's calculate the value of being in this state. And for that, we're going to need gamma. So let's say our discounting factor is a 0.9. And it'll make sense what a discounting factor is once we calculate this. So from here, just based on our intuition and because we know how this maze works, we know that the best possible action is go to the right, because from here we go here. So that means the maximum will be achieved when in this state you go to the right. And so let's see what happens if we plug it in here. So if you go from here to here, you don't get any reward. It will still be a 0. But then you'll get gamma, so you get 0.9 times the value of the new state, which is 1. So in this case, the whole result of this is 1 times 0.9 times 1 equals 0.9. So that's our value, 0.9. So if we calculate this now, you'll see that from here, we know, just by looking at the maze, we know, because we, as humans, because we're understanding how this equation works. Of course, an AI, the agent, would have to experiment with these things. But because we have like a crystal ball, we can see this whole maze. We have like the bird's eye view right now. We know that the best action is to go to the right. So if we plug it all in here, it'll be 0, no reward, plus 0.9 times the value in this state, 0.9 is 0.81. And so on. So here it'll be 0.73, and here it'll be 0.66. So you can see that the way the discounted factor works is it discounts the value of the state as you are further away. So if you're familiar with finance theory, then it's something similar to time value of money. Like, what would you think about it this way? What would you prefer, to have $5 today or $5 in 10 days from now? Just if somebody was to give you a choice, I will give you $5 today, or I'll give you $5 10 days from now. Well, of course, you would choose $5 today. Why is that? Well, because you can take those $5 and you can invest them at a certain interest rate, which is very similar to gamma, and your $5 in 10 days will actually grow into maybe $5.73 or something like that. And that's how time value of money works, and very similar concept here. And the important thing to understand here, this is just a theory, a way that reinforcement learning works. So Richard Bellman came up with this equation, and from then, now that's how we use it. So you could go ahead and come up with a different equation. It doesn't have to have gamma. It might have some other factor, might not even have a factor. But this approach works, and that's why we're using it. And this is what it visually looks like. So the further away you are, the less value of this being in this state. And in terms of time value of money, if I could say to you, where would you rather be? Would you rather be here? Or would you rather be here? You'd say, I would rather be here. So we're creating that same phenomenon as in time value of money. We're artificially creating it through gamma, so that in order to incentivize agents or inspire agents to be closer to the finish line. So if an agent were to be asked, would you rather be here or here? Because of the way this equation works, it would choose to be here. There's nothing more to that, nothing less. It's not something that the world works this way. No, it's just something that we're artificially creating in order for our agents to understand that this is this is good, this is good, this is good. They're all good, but this one is better than this one, and this one is better than this one, and this one is better than this one. And that way you can see the agent can see in which direction it needs to go. So it can see that if I'm standing here, remember that problem that we had, or was he standing here? Yeah, so if he's standing here, do I go down, or like if I'm standing here, do I go up or do I go down? Well, now it's not a problem anymore, because you can see that it's actually better to go up because the value is bigger here. And then from here it's better to go right because the value is bigger here than here. And then from here it's better to go right because the value here is bigger than here than here. And then from here, he already knows that he needs to go right because he'll get a reward here of 1. So that's how this whole approach works. Now let's have a quick look at the rest of the square. So how do we calculate the value in this square? Well, here is where things get a bit tricky. So from here, you might not actually go left, right? You might actually go right. So we can't just keep going like that because it might actually be shorter to go this way. So what we're going to do is we're going to calculate the value in this square first. And because obviously from here, the best way to go is up. Again, that's because we have the crystal ball, we can see things. And you'll see further down in this section, you'll see how the agent actually explores this, understands this on their, like through experimentation. But for us, we know that it's better to go this way. So we're going to calculate the value here. And that's why we're going to calculate the value in this square first. So here we have 3 possible actions. In reality, we actually have 4. We can also go left. The agent could hypothetically press left and bump into the wall and stay here. But for simplicity's sake, we're just going to show the actions that we, knowing what we know and having the crystal ball, we know which actions are the ones actually to lead to something other than the same state again. And so from here, we know that again, just because we have a crystal ball, we know that the best way to go is this way. An agent, of course, would have to experiment and find the best way. And you will see how that happens further down in the section. You'll see actually how an agent walks around and how you would experiment trying to find these values. But for us, we know it's that way. So here, if we plug everything in, 1, so the maximum, the best output is when you go up. Here's a 1, 0.9, 0. So you plug that in, you get 0.9. Okay, so we calculate that one. Let's calculate this one. Same approach. This is, you have 3 ways you can go. Actually 4 for the agent, but for us, we can see it's only 3. So 0.81. From here, you have 0.73. And it actually ties in nicely with this value, because then if you discount again, you get 0.66. And here you have 0.73 because this is the optimal route. So there you go. That is the values of all of these states. And now you can see that because we've created this equation, or we've created synthetically this whole concept of the closer you are to the finish line, the more valuable that state is. Now, because we've created that, now it's pretty obvious for the agent which way it should go. And we'll talk more about that in the coming tutorials. I hope you enjoyed today's session. And I know it might sound a bit very basic at this stage, but as we go through this section, we will add a bit more complexity to it. At the same time, if you cannot wait, if you want to jump into it, then there's a paper which you can look at. And it is the original paper by Richard Bellman. It's called The Theory of Dynamic Programming from 1954. And you can find it at this link. And there you go. So you can jump straight into it and read from the author of the Bellman Equation. But just bear in mind that this is quite a mathematically heavy paper. And on that note, I look forward to seeing you next time. And until then, enjoy AI.